Let's do the extra practice problems for Chapter 15. During a kinetic study, a student measures the rate of a chemical reaction to be 1.7 molar per second. To get this value, he measured the concentration of a reactant at 0 seconds and found that it was 8.01 molar. Later, he measured the concentration at 2.15 molar. At what time did he make that measurement? Okay, let's see what we know. We know they measure the rate of the chemical reaction, and we know that the rate equals 1.7 molar per second. And to get this value, he measured the concentration of the reactant. So we have the concentration of the reactant was measured at 0 seconds at 8.01, and that is time equals 0.0 seconds. Oh, and this is molarity. So far, that's our given information. Later, he measured the concentration. So this was the first concentration. Let's call it initial. The second concentration of this, we'll call it final in this particular instance, is 2.15 molar. And we want to know what, this is T initial, we want to know what T final is. That's what we're looking for. So that's our X. This is what he's asking for, is the time when this would be true. Now, you and I both know that R equals a negative concentration of the reactant over the change in time. And when we plug this in, we have the final, so negative, and I'm going to go like this, the final minus the initial and then the change of time is what we're looking for minus 0. That would be the final, which is what we're looking for, minus the initial, which is 0 seconds. Okay, and with that in mind, we know that this equals 1.7 molar per second. Okay, so now I'm going to get rid of the thing in between. 1.0 molar per second equals that. Okay, so now I'm going to multiply. I'm going to make this prettier. I'm going to multiply X up here, and then I'm going to divide both sides by this. So, and let's see what that top is. 3 significant figures, I get 5.86 molar divided by 1.7 molar per second. And I have 2 significant figures, so my answer has to be in 2 significant figures. These will cancel. Seconds. That'll be left with seconds. And so I know that at 3.4 seconds, that is when the concentration will be 2.15. And that's how we find that. Number 2. The kinetics of the following chemical reaction are studied. And we have HNO3 plus ammonia yields NH4NO3. So that's ammonium nitrate. The rate equation is determined to be, and there we have our orders put in. So we have rate equals K, and then the concentrations of each of the reactants, but there is no digit in the exponent place, so each of the orders must be 1 there. A, what is the order of the reaction with respect to the reactant HNO3? It would be 1 because there is no exponent written there, so it has to be 1. B, what is the order with respect to NH3? It would also be 1. C, what is the overall order of the reaction? Well, then you would just add up those exponents, so that's going to be 2. And what is the unit of the rate constant? So how we figure out that is R is always going to be molar per second. We're figuring out what the rate constant would be, and we know that we have each of these reactants to the first order, which means they're going to be n squared. I'll just rewrite it here for you so you can see it. So now we're going to divide both sides by that. So K equals m over m squared s. And this is going to cancel, so we'll be left with 1 over ms. So 1 over molarity per second would be the units for the rate constant in this particular situation, with both of them having an overall order of 2. That's what you would get. Number 3, the rate constant for a reaction is 0.781 1 over molar square S. What is the overall order of the reaction? Okay, here, I'm going to write this up here. Now we know that the rate equals K, A, X, B, Y. We know that, right? So I'm going to go M over S equals, this K is 1 over M squared S. So we want to know what the overall order is. So we're looking for this, aren't we? Okay. So when we divide this over here, we want to make it look like this. Because remember, that's the overall order. So we want so what would make that true? That's what we want. See, that's what we have, the units of the rate constant. We know rate is always going to be molar per second. So we're looking for the overall order. So what I've done is I've taken that and divided it to this side. That's what this is. Equals what we know the rate constant unit is. And so to make this true, x would have to equal 3, wouldn't it? Because if I put a 3 in there, and then I make it smaller, it's going to end up being that. When I cancel what I can, then I end up with my answer, and that's what I wanted. So the overall order of this has to be 3. This answer has to be 3 to make this true. Number 4, a chemist is doing a rate study of the following reaction, and he has the following data. What is the rate equation for the reaction, including the rate constant? Now remember, you're first going to look for your orders. First, you're going to write out your equation. Then you're going to look for x and y, which are the rate orders. And then once you have that, you're going to plug in everything to find k. And once you have k, the rate constant, then you're going to plug it all back in together. And that's your rate equation that he's looking for. So we start by writing the rate equation. R equals K, and then the first reactant is NO, and we're going to put that to the X power. And then the second one is H2, and we're going to put that to the Y power. Okay, so we're going to go about finding X and Y. So first, let's find X. So I'm going to see where I can hold Y constant. That would be trial 3 and trial 1. And so when I plug this in, and I'm going to do it the shorter version like I did in class, I'm going to go all the way to trial 3, all the way to the right for the instantaneous rate, because that would be, what I'm really doing is this equation divided by this equation, but with the 2 trials. So I'm going to go to trial 3, and I'm going to go 1.072 molar per second, and then I'm going to divide it by trial 1's instantaneous rate, which is 0.134 molar per second. We know that the K's are going to cancel. We know that the H2's are going to cancel because we specifically picked trial 1 and 3 so that they were the same and they'd cancel. So now I can go to trial 3 for NO, and its concentration is 0.100 molar to the X power. And then trial 1, it's 0.050 molar to the X power. And so this is going to equal 8.00, 3 significant figures, equals, this is going to equal 2 significant figures to the X power. And so for this statement to be true, X would have to be 3. Because 2 times 2 is 4 times 2 is 8. So X would have to be 3. So we're going to go up here, and we're going to put the 3 in for X. We figured out X. Now we're going to look for Y. And we've got to see where we can hold NO constant, which would be trial 1 and trial 2. So let's do that. Trial 1 and 2. We're going to get the instantaneous rate for 2, which is 0.268 molar per second, divided by trial 1, which is 0.134 molar per second, equals, now we're holding NO constant, so we're going to not use that. We're going to use trial 2 for H2, which is 0.040 molar to the Y, divided by 0.020 molar to the y. I have a strong feeling this is going to be 2 equals 2 to the y, but let's look. This is 2.00 because we have 3 significant figures equals. This is 2.0 because it has 2 significant figures to the y. What makes this true is that y has to equal 1. So I'm going to make that a 1. Now we've got the orders. Now we have to find the rate constant. So we're just going to plug in the whole first line. So the first line is 0.134 molar per second equals, we're trying to calculate the rate constant, NO here, the concentration is 0.050 molar, and that's cubed. And then H2 in the first trial is 0.020 molar, and that is to the first power. So we're going to figure out what this is. So this ends up being 2 significant figures, 2.5 times 10 to the negative 6th, and this would be molar to the 4th, K. Okay, so I'm just rewriting this and having worked out those numbers. And we're looking for K, so we're going to swing this over here and divide this number by this number. And that's going to give me in 2 significant figures, K equals 5.4 times 10 to the 4th. Now, what do we have here? We have molar per second divided by molar to the 4th. So that'll cancel. That'll be left with 3. So this will be 1 over molar cubed S. Okay, now we're still not done. So now we have to plug it into that equation. Keep that. So we're going to come up here and we're going to rewrite this with this K in here. Now obviously that could be rewritten this way, couldn't it? So it's your choice which way you wanted to write it. So first we calculated the orders, then we plugged everything in and solved for the rate constant, figured out the rate constant. Watch your significant figures as always. And then we plugged in the rate constant and the orders and rewrote it. So our final answer is this. And that's what he's going to be looking for on the test. Number 5, use the data in the table below to determine the rate equation, including the rate constant for the following reaction. So we're doing the same thing as we did in the last problem. We always start by writing this with our reactants. Then we're going to look at our trials and we're going to see, let's see where we can hold F2 constant. F2 is constant in the first 2 trials. So I'm going to go over and use trial 2 and the rate in trial 2, the instantaneous rate. Divided by the instantaneous rate of trial 1. And we know the K's will cancel. We know these will cancel because we've held it constant. So now we're going to look at the concentrations of those. And so in trial 2, the concentration for Xe is 0.300 molar and to the X power. And on trial 1, it is 0.150 molar to the X power. This is 4. Whoa, significant figures. 4, 2 significant figures. 0.0 equals, this is 2 to the X power. Okay, so when we do that, we can see, oops, and I should have given that 3 significant figures. Shame on me. To the X power. This is going to be 2, isn't it? So I'm going to come up here and I'm going to make X 2. It's to the second power. Now, we're going to look at where Xe is held constant, trials 1 and 3. And so I'm going to come back here and I'm going to do trials 1 and 3. So 3 is 0.0112 molar per second. There's trial 1. And now we're looking for F2. For trial 3, it is 0.300 molar to the y power over trial 1 is 0.150 molar to the y power. Okay, and so this gives us a 2. This gives us a 2 to the y power. I'm ditching my significant figures here because it doesn't seem to matter with the orders. So what makes this true? Y has to equal 1. So that means we just make it disappear. Y equals 1. We don't disappear the whole thing, just we make the invisible 1 take our place here, don't we? Now we're going to solve for k. And the way we do that is just I've plugged in the first trial. So the first trial, 0, 0, 5, 6. There we go. I plugged in the first trial. So this is k equals 3 significant figures. And this would be molar cubed. So now we're going to take that and we're going to take this number and divide it by this number. And that's going to give us k, isn't it? And that has 2 significant figures. And so that gives us a k that equals 2 significant figures, 1.7. Let's look at the units. R is that, so m over s, and then we have m cubed here. So we're going to divide this by m cubed because we're taking this and putting it over here and dividing. And so that's going to leave us, this is going to be squared. So this is going to be 1 over m squared s. And now we can take it back and put that into our equation. So we have R equals 1.7, 1 over m squared s. And then we have our orders there. So it's 2 significant figures, so my answer has to be in 2 significant figures. In the answer key, it's got 1.71, which is 3 significant figures. But this is given to us in 2 significant figures, and therefore I gave my answer in 2 significant figures, because if I take this and divide it by 3 significant figures, my answer has to be in 2. So that's why my answer looks like that. And it is different than what the answer is in the answer key. Number 6, a student is given 2 reactions to study. He is told that at room temperature, the first reaction has a rate constant of 1.341 per molar second, while the second has a rate constant of that. He is asked to measure the activation energy of each reaction at room temperature and use that to determine which rate constant belongs to which reaction. Once he measures the activity energies, how will he determine which rate constant belongs to which? Well, the one with the lower activation energy should have the highest rate, and so the highest rate constant. And so the one with the lowest activation energy should be the rate constant of 1.34 with the units, and the one with the higher activation energy should be the smaller number, the smaller rate constant, which is 0.145, and then the units. Number 7. Given the following reaction mechanism, and it gives us that, what is the catalyst and the overall reaction? Okay, there is our reaction mechanism. Now, first off, let's find the catalyst. The catalyst goes in at the very beginning and out at the very end the same. So there's only one guy that's here, here, and here. That's the very beginning, that's the very end. You're looking for the catalyst, it's going to be the same both places. There's only one guy that is water. H2O is the catalyst because it's going in and coming out the exact same way. So water is the catalyst. The next question was, what is the overall reaction? Well, to find the overall reaction, we take the catalyst out and we take out anything that goes in and comes out. So this goes in, it comes out here, but it goes in here, right? This comes out here, but it goes in here. Let's see. This comes out here, but it goes in here. So now we've gotten rid of everybody that is not a catalyst or that didn't go in and out or go out and in. So we've taken care of that. So what's left? We have ClO minus plus, okay, and everything else there is wiped out. This Br minus yields Cl minus plus BRO minus. And all I've done is taken what's left. So this guy isn't crossed out, he's a reactant. This guy isn't crossed out, notice it's a reactant, so he's a reactant. This isn't crossed out, so that's a product. And this isn't crossed out, so that's a product. So that would be my overall reaction from this catalyzed reaction mechanism. And it doesn't matter, the commutative property applies, so it doesn't matter if they're flip-flopped. Number 8. Is the catalyst, and number 7, a heterogeneous or a homogeneous catalyst? If we're given a reaction mechanism, and that means it got involved in the actual products and reactants, then we know it is a homogeneous reaction catalyst. If it was a heterogeneous catalyst, it wouldn't have a reaction mechanism because it just helped the proximity of things to be closer together so it'd have more effective collisions rather than actually getting involved in the chemical reaction. So we know it's a homogeneous catalyst. Number 9, consider the coordinate diagram below. So there we have the coordinate diagram. Draw the coordinate diagram for the same reaction being run under the influence of a catalyst. And so basically, your reaction should just look like that. And notice that originally it was up higher, I just made it smaller. So anything showing a smaller activation energy would show that this had been catalyzed. This reaction would have been catalyzed. Remember that this number and this number should be the same as what is actually in your original diagram. What the difference will be is the actual activation energy. Number 10, a chemical reaction has both gases and liquids as a reactant. If a heterogeneous catalyst is used to speed up the reaction, what phase is it in? It would have to be in the solid phase, because if it was in the liquid or the gas phase, then it would be the same phase as one of the reactants, and therefore it would be a homogeneous catalyst. So to be a heterogeneous catalyst, it's got to be in a different phase than either of the reactants, which means it would have to be a solid. Guys, work very carefully on this chapter, and I know it's a lot of work. Show all your work, study for and take this test, and then read the first half of the next chapter. Have a very blessed week.